So today we want to discuss a case which in principle should be the easiest, but has a number of subtleties. So let's go through them carefully. But before we start the lecture, let me remind you the basic program involved in solving the Schrodinger equation. So given any potential or any force, this is the series of steps that you usually take to solve the Schrodinger equation. Our goal, remember, is to solve the time-dependent Schrodinger equation. Solve the time-dependent Schrodinger equation, right? And you do this by looking at separable solutions, right? So you write psi of xt as, you write psi of x comma t as something that depends only on x and something that depends only on time. And you can solve for the time dependent part quite easily. And this turns out to be minus IET over h bar. So these are states with definite energy. And to get f of x, you need to solve the time. So solve the time independent Schrodinger equation to get f of x. Okay. Now you construct the this is the first step. This is the second step. And this is the third step. Construct the general solution. The general solution, because of the linearity of the Schrodinger equation, is a superposition of all the separable solutions with some coefficients. Psi n of x. So instead of f of x, I'm calling it psi of x. So, okay, I don't want to use the same symbol. E to the minus IENT over h bar. Okay. Depending on how many separable solutions are there, the sum will involve that many terms. So the only thing that is not known at this stage is Cn, and Cn has to be set by you by looking at certain initial conditions. So the problem is, say, for example, that the initial condition at time t equal to 0, psi of x comma 0 is some function, let us say h of x, right? Now you should appeal to this initial condition and use the fact that the science are orthonormal. Now the science would be automatically orthogonal because remember the science are the solutions of the time independent Schrodinger equation, which is h psi n equals E n psi n, and h is a Hermitian operator. So you are guaranteed that the science would be orthogonal to each other. You can also normalize them properly so that the set is orthonormal. So the science can actually be used as a basis set. Okay. So use the fact that the science are orthonormal to fix the expansion coefficients Cn. So the Cn's which remain to be found can be easily found out. Take this general solution and multiply both sides of this general solution by psi m star. So psi m star of x and apply it to time t equal to 0. At time t equal to 0, the left hand side is psi of x comma 0, a function that is given to you. It has to be given to you. The right hand side is sum over n. I'm multiplying by psi m star of x, psi n of x. There is a Cn. And at time t equal to 0, the exponential factor simply becomes 1. Okay. Now I will integrate both sides of this equation with respect to dx. Equals, I can pull out the summation because the summation, the integration over x have nothing to do with each other. And I can pull the Cn's also because they are constants. This problem. Psi m star of x, psi n of x. But remember, because of the orthogonality of the size, this is basically delta nm. This is equal to 0 if n is not equal to m, and equal to 1 if n equals m. So ultimately, the right hand side, which is a sum over all different Cn's, boils down to one particular value, which is n equals m. So you get the nice equation that the expansion coefficients are given by integral dx psi of x comma 0 psi m star of x. Okay. So once you know what the expansion coefficients are, you can figure out what the general solution of the Schrodinger equation is, and everything is done. This is the program that you follow to solve the Schrodinger equation given any force, given any potential, as long as the potential is time independent. We will tackle the question of how to deal with time dependent potentials in the next semester. It turns out that this is actually a very hard question, and one has to resort to certain approximation methods, and we will develop one particular approximation method called the time dependent perturbation theory next semester. But for time independent potentials, this is the series of steps that you follow to solve the Schrodinger equation. Okay. All right. So with that said, let us shift gears and start talking about the free particle. The free particle, as you can readily see, should be the simplest case. Free particle means that there is no force acting on the particle. Excuse me. Implies there is no force. Okay, which means the potential is basically a constant, which I will take to be 0, because I can always shift the potential. So the potential is 0, which means the time independent Schrodinger equation, which is h psi of x equals E psi of x, which I will write in the position x representation, would be h is kinetic energy plus potential energy, but potential energy in this case is 0. So this equation simply becomes minus h bar square over 2m d square psi over dx square equals E psi of x, okay, which I can rearrange slightly and write d square psi over dx square equals minus 2me over h bar square times psi of x. And this factor 2me over h bar square, I'll call some k square to make this into an equation that you know very well, a simple harmonic equation. Okay, that's pretty much it. And you know what the solutions are. It's very, very simple, and obviously everybody knows this. The solutions are either sine kx plus cosine kx or e to the ikx plus e to the minus ikx. I will choose the e to the ikx route. So I will write the solution to this equation as I of x equals a e to the ikx plus b e to the minus ikx. Okay, where k square, I remind you, is, or rather, yeah, k square is 2me over h bar square. So the way I've written, k can be either positive or negative, because k is plus minus square root of 2me over h bar square, and e is obviously positive. So k can be plus square root of 2me over h bar square or minus square root of 2me over h bar square. Okay, so this is the separable solution. Sorry, this is the these are the stationary states. So what is the complete solution? The complete solution is basically I need to tag on the energy dependence. So both of these solutions, e to the ikx and e to the minus ikx, have energy E, obviously. So psi of x comma t is a e to the ikx times the energy. Remember, the solution, the general solution is psi n of x times e to the minus I e t over h bar, right? Take off all these wiggly lines. So I should tag on the time dependence. So the time dependence is minus I e t over h bar plus b e to the ikx minus ikx e to the minus I e t over h bar. Okay. Now since k square is 2me over h bar square, k square is 2me over h bar square, I can rewrite this to write e in terms of k. So I don't have two different variables. I have only one variable k, which is equal to h bar square k square over 2m. So my psi of x comma t for the free particle is, when all is said and done, a e to the, if I pull out the ik, I get x minus h bar k over 2m times t plus b e to the minus ik x plus h bar k over 2m times t. Okay. So this much should be rather easy because everything is straightforward. It's a very simple simple harmonic is oscillator differential equation. So it's tempting to conclude that we are pretty much done with the solution of the Schrodinger equation. But there are a bunch of problems in this. The first problem, or rather comments. Okay. The first comment is something that is known to you in a different guise, and that is the fact that this wave function is not normalizable. Okay. What does this mean? It means that if I construct psi star of x comma t, psi of x comma t dx, or even if I construct just psi star x, psi of x dx, none of those exist. Okay, they all blow up because the dependence is purely oscillatory. E to the ikx, psi star psi would be just 1. So integral dx between minus infinity and infinity is a nonsensical quantity. So this cannot represent probability in any sense. So this quantity is not defined. So this psi is not normalizable. This itself should not be surprising to you because we have already discussed that the eigenfunctions of the momentum operator are not normalizable, right? So what does this mean? This means that h in this case is just p square over 2m. So the time independent Schrodinger equation is basically p square over 2m psi equals E psi. And psi is an eigenfunction of p square, which means psi is also an eigenfunction of p. So which is obvious that psi is not a normalizable eigenstate. So which means that for the free particle case, even though the solution is very simple, we have the rather disappointing fact that the stationary states are not normalizable and hence cannot be physical states. Okay. So somebody is asking me why psi is, or can you explain why psi is not normalizable? So take the stationary state. The stationary state is psi of, okay, let me actually explain this in a slightly different fashion. Okay. So remember that we wrote psi of x comma t as a e to the I k x minus h bar k over 2mt plus b e to this guy, right? Now k can be positive or negative. So in this way of writing, I've assumed that k is manifestly positive, but I can combine both of these solutions into one single solution. Psi of x comma t is a e to the exponential ik times x minus h bar k over 2m times t, and I will account for both k equal to k, sorry. I'll account for the fact that k greater than 0 is wave traveling to the right and k less than 0 is wave traveling to the left. Okay. So instead of having two different solutions, a e to the I plus ik minus ik, I will simply put k as negative, positive and negative both, instead of assuming just k is just one thing. Okay, this means I can account for both wave going to the left and right. Both equation 1 and equation 2 are equivalent. You can use either one of them. So to show that psi is not normalizable, take psi star xt, psi of xt dx. Okay. What is psi star? Psi star is obviously a exponential minus ik x minus h bar k over 2m times t. Okay. So what is psi star psi? Psi star psi is basically, sorry, a star. This is just mod a square. So if I calculate psi star psi dx, this is just integral minus infinity to infinity dx, which is obviously blowing up, and hence it is not a normalizable wave function. Okay. So I hope that was clear. So can you please explain how k can be negative? So at this point, k is a variable which we usually refer to as the wave vector, right? Now in 3 dimensions, this is actually a vectorial quantity. So basically what I'm trying to tell you is this. So when you write down the solution of a wave equation, remember that what is a wave? When I say something is a wave, I mean that it is a function of x plus minus vt, right? So for example, you learned that sine of, what is this? X minus vt, sine of x plus vt, e to the ikx plus minus vt. They're all waves. As long as you have a function that is a function of not x and t in a slightly different fashion, but x and t combined in this particular fashion, x plus minus vt, then it is a wave. So when I have sine x minus vt, I mean that it is a wave traveling to the right. And when I have sine x plus vt, I say that this is a wave traveling to the left. So here in equation 1, if I assume k is manifestly positive, then I can identify h bar k over 2m as velocity. And so the first part is a wave traveling to the right, and the second part is a wave traveling to the left, because it is x plus vt, right? But if I assume that k can be both positive and negative, remember that I don't need the b part. So if you just concentrate on the first part, which is e to the ik x minus v, x minus h bar k over 2m times t, if k is positive, it is a wave traveling to the right. If k is negative, then it becomes x plus h bar mod k over 2m times t, which is a wave traveling to the left. So I can account for both waves traveling to the right and traveling to the left by making k both positive and negative. That is what I mean. Any other questions? Okay, good. So I will erase this part. Now remember, I'll erase this part. I hope this was clear. Okay, now the second comment. Now the first comment itself is a showstopper. If a wave function is not normalizable, we really have to think deeply about what do we mean by stationary states. We'll come to that question in a second. For now, I want to highlight one other small point. Remember, look at the solution. If you look at the solution, it's obvious that whatever multiplies t is the velocity, right? This guy is the velocity. But what is the velocity? The velocity is h bar k over 2m. Now momentum p is h bar k, right? So this velocity turns out to be equal to momentum over twice mass, which can be a little strange to look at, because classically, if this particle were a classical particle, how would I describe it classically? What is the equation of motion? The equation of motion is md square x over dt square equal to 0, which means dx dt is a constant. This is the velocity. What is the velocity classically? It is just momentum over mass. So V classical is momentum divided by mass, but the velocity of this quantum mechanical wave is actually half the velocity of the corresponding classical particle. So what does this mean? Why is it that quantum mechanics tells you that the velocity is only half of what you expected classically? This also doesn't make sense. If you assume that momentum is h bar times k, which is obviously correct, because that is what we have been using all along, and obviously k and p are related through just h bar. So this relation has to be correct. And the solution of the Schrodinger equation automatically gives you this h bar k over 2m. So this v is also h bar k over 2m. So then the velocity of this quantum mechanical wave is half the velocity of the corresponding classical particle, which also is a little strange. So we want to explain this fact also. Okay. All right. Now the third rather interesting question that we can ask is, look, you have constructed a wave. Now, ultimately, I can understand what a particle is. So how do I understand what a particle is? Particle is something that is there at, let us say, x is equal to 5 centimeter. There is a small round spherical object that is a particle. I can always claim that. So a particle is a localized entity in space, right? So a particle is a localized entity in space. A particle is not spread out over all of space, right? You and I can also be viewed as particles, rather big particles, but okay, composite particles. And we don't exist all over India, right? We exist in a very, very specific, right now I am sitting on my chair in my office. So I am in a very, very localized portion in space. So whenever you have a particle, you should be able to explain the particle as being something that is there at that particular position, one particular position. Of course, there is a confusion due to uncertainty principle, but as long as I don't care about the momentum of the particle, I should be able to say that the particle is right there, localized in space. But here I have a solution that is manifestly a wave. A wave is, by definition, not a localized object. A wave, a free wave like this exists everywhere. E to the ik times x minus h bar k over times time t exists everywhere. So with this highly delocalized object, how am I going to explain a highly localized object like a particle? So I have these three questions that I want to understand when I talk about a free particle. Even though the solution of this free particle, mathematically, it is very, very simple. Physics-wise, it throws up a lot of different questions that we have to answer. Okay, so we will proceed to answer them. But before I answer them, do you have any questions about anything that we have discussed? So I will complete this thought. A wave is highly non-local. A wave is an extended object. So how does this describe a particle? That is our question. Okay. Okay. So we want to understand how quantum mechanics answers these questions. Now notice that there is no wiggling out of these facts. It is obvious that the way we have written it, psi of x is not normalizable, so it cannot be a physical wave function. It is obvious that these stationary states, therefore, are not physical states. It is obvious from looking at the solution that the velocity of this wave is half the velocity of the classical particle. And it is also obvious looking at it that we have an extended object and not something that is localized. So our questions, the way we have posed them, are not wrong. They are perfectly valid questions. So we have to find answers to these questions within the framework of quantum mechanics and within the framework of this program that I have sketched at the beginning of this lecture. So what have we done? We have done the first step. We have solved for this time-dependent Schrodinger equation by piecing it up into a spatial part and a time part. We have found out that the time part is just e to the minus iet over h bar. We have done the second part also. We have done the time-independent Schrodinger equation solution, and we have gotten these stationary states. But what we have not done yet is step number 3, which is constructing the general solution. So our hope, our desperate hope is that somehow step number 3 can cure all these problems that we have discussed. Step number 3 is basically telling you that the most general solution is a linear superposition of all the stationary states. So how does a linear superposition in principle cure all these problems? So I want to answer this question first a little quantitatively by looking at a very simple example as to what a linear superposition of waves means. Linear superposition of waves. Okay, so let us look at a very, very simple example and construct this linear superposition. And this example will give us clues as to how we are going to solve these different problems. So let's take a very simple example. I will take two waves. The first wave, excuse me, wrong color. The first wave, which I will call psi 1, is, I'll take it to be sine k1x minus omega 1t. And my second wave, psi 2, which is also a function of x and t, obviously, and not any random function of x and t, a function of kx minus omega t, or equivalently x plus minus vt. Psi 2 I will take to be sine of k2x minus omega 2t. So these two waves by construction have different wave vectors and different omegas, which means they have different velocities. Excuse me. Okay. Now I've chosen them to be propagating in the same direction. I don't have to, but I've chosen them for convenience. And also for convenience, I've chosen the amplitude for both these guys to be 1. So they are both waves of unit height. Okay, again, this fact is not very important, but it makes my mathematics a little easier. Now I will construct a linear superposition of these guys. I'll simply add them. This is one example of a linear superposition. Sine k1x minus omega 1t plus sine k2x minus omega 2t. Okay? And I will use the formula that sine A plus sine B can be written as 2 cosine A minus B over 2 times sine A plus B over 2. I hope that is right. To write the psi of x comma t as 2 times cosine A minus B. My A is k1x minus omega 1t and my B is k2x minus omega 2t. So if I subtract them both, I get k1 minus k2 over 2 times x minus omega 1 minus omega 2 over 2 times t times sine. If I add them, I get k1 plus k2 over 2x minus or plus minus omega 1 plus omega 2 over 2 times t. Okay. All right. So notice that now the addition of two waves looks like a very different object. It is a multiplication of a cosine function and a sine function, but the cosine function is also a function of x minus vt, and the sine function is also a function of x minus vt. So this is also the first guy here. This is also a wave, this is also a wave. But what kinds of waves? What are their velocities? Notice that the first guy is proportional to k1 minus k2 and omega 1 minus omega 2. The second guy is proportional to k1 plus k2 and omega 1 plus omega 2. So I will define k bar as the average of these guys, 1/2 k1 plus k2, and I will define omega bar as 1/2 omega 1 plus omega 2. And I will define the difference to be delta k, which is 1/2 k1 minus k2, and I will define the difference delta omega, which is 1/2 omega 1 minus omega 2. If I carry the 1/2, I can write the psi a little easier. So psi of x comma t would simply be 2 cosine delta k x minus delta omega t times sine k bar x minus omega bar t. Okay. Now I did not say anything about the values of k1 and k2 and omega 1 and omega 2, but right now I will make a choice. I'll make a choice that k1 and k2 are very close to each other and omega 1 and omega 2 are very close to each other. In other words, I will choose, I'm the one that is doing the adding. I can take any wave I want to. Nobody can stop me. So I will choose waves whose velocities are very close to each other. Okay. In other words, I will choose k1 is approximately equal to k2 and omega 1 is approximately equal to omega 2, which means that if k1 and k2 are close and omega 1 and omega 2 are close, the average k bar is much greater than delta k. Because if they're very close to each other, k1 minus k2 is a very small quantity. Also, omega bar is much greater than delta omega. Okay. So now if you look at it this way, then this addition, linear superposition of two waves gives you a product of two waves. The first wave has a very long wavelength and the second wave has a very short wavelength. So the first guy has a very long wavelength, and the wavelength of the first guy is equal to lambda L is 2 pi over delta K. Okay. And the wavelength of the second guy, which is very, very short, is 2 pi over K bar. Assuming K bar is large enough, lambda S will be very small. And if delta K is very small, as we have chosen, the corresponding wavelength will be very large. Okay. I hope this is clear. If there is any questions, please ask. So what would this capital Psi of xt look like? Suppose if I graph it. Well, if something has a very short wavelength, then it goes up and down very fast. If something has a long wavelength, it sort of goes up and down not very fast. So if the product of these two waves looks a little interesting. It looks like, so if I draw it out, let me try my best. Having an iPad helps because it makes me not suck at sketching. Because I can draw straight lines. So one of these guys has a very short wavelength, so it keeps going up and down very fast like this. Okay. The second guy with a longer wavelength is the envelope of the first guy. So I'll use a different color if that would make it a little better. I don't know if it would, but I'll try. Again, this is the envelope of the first rapidly oscillating wave. Okay. So this is what my psi of x comma t looks like. So I've only drawn the spatial part, but I hope, I've only drawn the wave qualitatively, but I hope that is clear. So what is it that we have constructed? What is this very simple example of a linear superposition of two waves? What does it represent? Well, it represents something that you know about waves. If I add two waves, the waves can add constructively or destructively, right? So if you look at the envelope of these two waves, concentrate on the red curve has points where it is large and points where it is very close to zero. So the points where it is very close to zero are the points where these two waves are adding destructively, and the points where it's a maximum are the points where it is where the two waves are adding constructively. So the first clue is that when I add two waves, I can create regions in which the wave is effectively zero. Okay. Now, remember the question of localized objects. When I want something localized, I don't want something that is propagating all over space. I want something that is a very, very small packet that is traveling in space and time. So I want something that looks like this. So let me draw this again. Suppose if I manage to construct something that looks like this. Okay, that is it. Nothing else. I don't want a whole, oh, sorry, this is not showing. So I'll stop share and reshare. So please ask if there is any questions as I'm doing this. Okay. So the hope is that if I add not just one wave, but many waves, I can in principle construct something that doesn't look like the first picture, but rather looks like the second picture. Okay. And this, I have no problems with identifying this with a particle because this is a very localized object. by adding a whole bunch of waves in a very, very particular fashion such that they cancel out at all regions of space except a very, very small region of space. I've created, instead of a wave, I've created what is called a packet of wave, which is called, unsurprisingly, a wave packet. And this wave packet I can identify with a particle, because this, even though wave itself is an extended object in space, a wave packet is a localized object in space. So in pictures and qualitatively, this is what we are trying to do. So the linear superposition of different waves can move us from the region of constructing waves to the idea of constructing wave packets. Of course, this is easier said than done. We have to construct the linear superposition very, very, very carefully such that we do get this, okay? And we will see that the choices are actually quite limited. So this is how qualitatively I can get rid of the problem of localization, of trying to explain why it is a particle, how come a wave solution can explain a particle. A wave itself cannot explain a particle, but if I add up a whole bunch of waves very carefully in a very precise particular fashion, I can create a wave packet which can mimic a localized object in space, okay? So this is how I solve problem number 3. Now, how do I understand problem number 2, which is the fact that the velocity of the quantum mechanical wave was half the velocity of the original particle? Well, again, let me look at this very simple example of adding 2 different waves, okay? And then we can extend this to a linear superposition later. So remember that this adding of 2 different waves, we are adding 2 different waves with 2 different velocities. So let us actually look at what these velocities are. There is one wave that is traveling around with a very short wavelength, which corresponds to the wave vector delta k, and one wave which is very long wavelength corresponding to wave vector delta k, and one wave with a very short wavelength corresponding to wave vector k bar. So obviously, since the velocities and since the omegas and the k's are both different for these 2 waves, they should correspond to 2 different velocities. So what are these velocities? Let me call the velocity of the guy traveling with wave vector k bar and angular frequency omega bar as Vp. Vp is omega bar over k bar, okay? And this I will call the phase velocity. And the other guy with a big wavelength, I will call this as Vg, and this is the corresponding angular frequency delta omega over delta k. And this guy I will call group velocity. So these are the 2 velocities of the 2 different waves that constitute the linear superposition in our simple example. Now let us move further and try to understand what this is. Now omega bar, so Vp, which is omega bar over k bar, I can write this as, and I can multiply and divide by h bar and write this as h bar omega bar over h bar k bar. And h bar omega bar is just the corresponding classical energy. And this is the classical momentum. So I can write this, as E over P, right? Now what is E? E is 1/2 mv square classically, and P is mv. So obviously this is V over 2. So again, we get the same V over 2 we got in our original solution to the Schrodinger equation, right? We understood that, we realized that there was a problem with this solution, and one of the problems was that the velocity of this wave is not V as you would expect a classical particle to have. It is actually V over 2. So why is it that the quantum mechanical description is giving us a very different velocity? It turns out that the quantum mechanical description is not giving us a free velocity. We were just measuring the wrong velocity. We were measuring what is called the phase velocity of the wave. But what we should actually measure is the group velocity of the wave. This guy. Why? Well, assuming that if delta omega and delta k are very, very small, then I can approximate this by the corresponding differential, d omega over dk. Agree? So what is d omega over dk? Well, again, I can write this as, so before I write this as d omega dk, I can multiply and divide by h bar, and I can write this as h bar delta omega divided by h bar delta k, and I can write this as h bar delta omega is just dE, and h bar delta k is just dP, right? So in the limit that delta omega and delta k are very small, which is the limit in which we are working, this can be written as dE over dP. But what is E? E is, classically we expect E to be, or even quantum mechanically, it is just P square over 2m. So dE dP would be just P over m, which is the velocity. Okay. So where did we go wrong in our original description? In our original description, remember that we only constructed one wave. Okay, and this wave corresponding to equation number 2, which was the solution of the Schrodinger equation, corresponds to, in our simple example, the wave that is going around very fast, the wave that is going around with a very large wavelength, okay, k bar. What we should actually measure is the group velocity of the wave, or rather the envelope of these waves. The envelope of these waves, which is a group velocity, has the correct velocity v that corresponds to the velocity of the classical particle. So why is it that we did not see it in this particular solution of the Schrodinger equation? Well, we did not see it because we constructed only one wave. We did not construct a linear superposition. When we construct a linear superposition, then we will naturally have two different velocities that we can choose. The phase velocity of the waves, which is the average velocity, which is the omega bar over k bar, or the group velocity of the waves, and it is the group velocity of the wave that should be identified with the corresponding classical velocity of the particle, because it is the group velocity that creates this particular wave packet which we identify with the particle. Okay, so even this very simple example of linear superposition of two waves helps you to understand how to get rid of problems number 2 and 3. The question of problem number 1 is also a little subtle at this stage, but essentially what we have to do is that we have to ensure that the linear superposition is a normalizable solution. Okay, so remember that the construction of linear superposition, at least qualitatively, helps us to understand where is the particle and what is the velocity of the corresponding particle. So we have to construct the linear superposition. Construct the linear superposition such that psi of x comma t is normalizable. This remains to be done. Okay, so now how many waves do we need to construct this superposition? Remember that adding just two waves would not give us anything that looks like a wave packet as you see in the second diagram. So we have to add many different kinds of waves with many different kinds of k. But the solution of the Schrodinger equation places no restriction upon the values of k that you get. Okay, this is a very important difference, and I will talk about this difference when I talk about potentials in general. There is a difference between what are called bound states and difference between what are called scattering states. This is not a bound state solution. Usually in bound states, you have certain discrete values that the energy or correspondingly k can take, and this is because there are boundary conditions. There are no boundary conditions in this problem. The wave can go as far to the left as it wants and as far to the right as it wants. So there is no boundary conditions. There is nothing stopping the wave as such, right? So the absence of boundary conditions means that the energies are not quantized. The energy can be any continuous parameter. Correspondingly, k can be any continuous parameter, which means we have at our disposal all different values of k, an infinite number of values of k. So we have to construct the wave packet by taking the linear superposition of all these infinite different values of k, which means our linear superposition will not be a sum, it will actually be an integral. Okay, so linear superposition, excuse me, superposition of an infinite number of waves. Okay, so this will be an integral, not a sum. In particular, it will be an integral over k. So there is a question. So for your assumption of taking k1 and k2 to be very close to each other to be applicable in our case of free particle, we need infinite number of waves. Yes, so luckily that is exactly what I was trying to explain right now. So don't go too much by this particular example. This is just one very simple illustration of what a linear superposition can buy for you. Okay, this is not a realistic example, whatever I have discussed here. This obviously is not a free particle. The first wave is not a free particle. The second wave is. So the first way was just to explain that there is a way in which, by using the destructive properties of wave addition, that we can actually construct something that is localized in space. Okay, so yes, we do have. If we want to construct a wave particle, we do need infinite number of Ks, and we have to choose the expansion coefficients of all these waves very carefully. And it is also clear that the expansion coefficients cannot be constants. So suppose if I take psi as some a1 sine k1x minus omega t plus a2 sine k2x minus omega 2t, blah, blah, blah. If a1 and a2 are all constants, then it is very hard for me to adjust them such that all these guys add up destructively to give me something localized in space. So the quote-unquote constants a1, a2 should also be chosen very carefully, and I will explain how this is done in the next lecture. Okay. So for now, I just wanted to sketch a qualitative way in which this can actually be achieved, and all these problems can in principle be cured. Okay. So that is what we would need to do, and that is what we will do in the next class. We will construct a linear superposition of all these stationary states, and these stationary states themselves are not physical states. They don't reside in the Hilbert space, but we have to construct a linear superposition of these states such that it actually lives in the Hilbert space and it is actually a normalizable solution. And this task we will take up in the next lecture, and we'll also talk a little bit about the uncertainty principle as it applies to the linear superposition of waves. Okay, so for today I will stop, and please ask me if there is any questions now.